For this AP Physics 2 project, I, along with John Losey, am going to show and explain the ideal gas law, which is pressure times volume is equal to the moles of gas times a constant times the temperature of the gas in kelvins. And so how we're going to be doing this is we're going to be using a glass bottle with a balloon on top, and we are going to freeze the bottle, and then it's frozen right now. I'll demonstrate for you. The balloon is totally flaccid. There's no air in there at all. And basically what we have here is like a cylinder with a movable piston on top, where when the gas heats up inside, when we put it in the warm water, the gas will heat up, and it should expand and take up this new volume up here, and we'll be able to see that when the gas rises and fills up the balloon. Alright, so now we have our water in the bowl. It's quite warm, and we're about to put the bottle into the bowl, which will allow the gas inside the bottle to heat up. Once again, we have the balloon here. It is totally empty, not filled with gas at all, and we should see a change after we let it sit for a minute or so. You can already see the gas at the neck of the bottle starting to fill up the balloon. The gas is starting to fill up a little bit already. You can see even now as I press it, it's not, there is definitely a gas bubble in there. It is occupying the new volume as the ideal gas law would predict, and now we can see completely that there is, when I squeeze it, there is definitely air inside of there. So now we're going to have John Losey. He's going to explain the math behind it using the ideal gas law.
Wow, that was something else, Bryce. Good job. Now, let's dive into why this phenomenon happens and how the ideal gas law helps explain this. Again, the ideal gas law is pressure times volume equals the number of moles times the ideal gas law constant, which is R, times temperature. Using this equation, let's find out the pressure of the air inside the bottle before we place the bottle in the hot water. So to start, since the bottle is frozen, our temperature is going to be about 32 Fahrenheit, which would be converted to 273 Kelvin. Bryce had a 12-ounce bottle, so we'll say our volume is equal to 3.5 times 10 to the negative fourth meters cubed. Our N is going to be 1.4 times 10 to the negative second, and our R, which is a constant, is 8.31. Alright, so we can rearrange our equation to have P all by itself on the left side by dividing each side by the volume. And now we can just fill in the numbers to find the value of P. Once we put all that in there and we calculate the pressure should come out to 94 kilopascals. Now this is the pressure of the air inside the bottle before we put it in the hot water. Now let's see what the pressure is going to be when we put the bottle in hot water. And the only thing that is going to change from our original equation is the temperature. The temperature is going to increase. So our new temperature is going to be 310 Kelvin instead of 273. Now we can go back to our Pfeffner equation and just plug the numbers back in again. 3 10 Kelvin times 8.31 times 1.4 to the negative second, all that over 3.5 times 10 to the negative fourth. And when we do the math, our new pressure of the air inside the bottle after we put it in the hot water is 103 kilopascals. This increase in pressure is the reason why the balloon inflates on the bottle, because the particles, they start moving faster and they start spreading out, and so they start to go all over, and that includes the balloon too. Now, in our experience, some of these numbers aren't quite exact, so the pressures that we get aren't the actual pressure that was inside the bottle, but you can kind of see how the pressure rises when you increase temperature. It's a direct relationship, and also the balloon wasn't airtight; it wasn't sealed all the way, so some air could have got out. It wasn't perfect. Hope you guys learned a little bit more about the ideal gas law. Thanks for watching.